In this video, we're going to take a look at the 2003 multiple choice no calculator section, and we're going to begin with number 76. A particle moves along the x-axis so that at any time t, its velocity is given by a velocity function of 3 plus 4.1 cosine 0.9 t. Our job is to find the acceleration of the particle at t equal to 4. So, in other words, if we're going to find a of 4, that is equal to v prime of 4, and we're going to let the calculator do the work for us. So I'm going to bring the calculator up. So this one's definitely a calculator question, and so I'm going to clear that out of there. And remember that your function for finding the derivative is math 8. You should know that very quickly. I'm finding the derivative of the function 3 plus 4.1 cosine of 0.9x. Type very carefully because one little slip can mess you up. In terms of x at 4. Depending on your calculator, you'll use whatever syntax your particular calculator requires. I press enter, and I know that the derivative of velocity is 1.633. which is letter C. So that's 76. In number 77, they are telling us that the regions A, B, and C, so here's A, here's B, here's C, in the figure above are bounded by the graph of F and the x-axis. If the area of each region is 2, so in other words, this region in A has an area of 2. The area for B also has an area of 2. And the area of C also has an area of 2. What is the value from the net area from -3 to 3 of f of x plus 1? So we're going to use our integral properties to break this into two integrals. So I would go from -3 to 3 of f of x dx plus, and then I'm going to do another integral from -3 to 3, and I'm not going to try to write the -3 and 3 again, of 1 dx. All right, so now I will write it. So from -3 to 3. So this particular piece we know is a rectangle that is 1 unit high, and from -3 to 3 is a span of 6, so the area of that part alone is 6. And then we're going to have to add that to the accumulated area, the net area that we get from -3 to 3 of f of x dx. So the net accumulated area from -3, remember we're starting at -3 and we're traveling to the right, so this area is going to be counted as a negative. So that's going to be -2. And then the next region is above the x-axis, so that's going to be counted as a +2, so they're going to undo each other. And then the next region is below the x-axis, and that's going to be -2. And if you combine that, -2 and 2 is 0, -2 gives you -2. So we have -2 plus the 6 gives me a total net area of 4. So the key here is using your integral properties to do that problem. In number 78, the radius of a circle is, I'm going to make this a little bit smaller, the area of the circle is increasing at a constant rate. So notice what was just stated is dr, and remember we read with our pencil, with our eyes, and with our minds. So dr dt is 0.2 meters per second. Okay, so that's what I got right here, radius rate. There it is right there, radius rate. The question is, what is the rate of increase of area. So what they're asking me to find, and you just got to read this, you can do it, find dA dt when C circumference is equal to 20 pi. Okay, so let's focus on what our job is. Remember, our job in this problem is to find dA dt, and we are dealing with a circle. So let's begin with the area of a circle. We know that the area of a circle is equal to pi r squared. And when I take the derivative of both sides, I get, on the left-hand side, by implicit differentiation, I get dA, whoops, I left that in the exponent mode. I get derivative dA dt is equal to, on the right-hand side, we're going to use the power rule, and we're going to use implicit differentiation. So I get 2 pi r, looks like a word, but you get it, dr dt. Now, let's get this, I'm going to slide that r over just a little bit. So 2 pi r dr dt. Let's come back over here to circumference, and let's talk just a minute. Think back to what you know about geometry. 2 pi r. Well, 2 pi r, as you know, is the formula for circumference of a circle. So if I come back over here to my text, if circumference is 2 pi r, I'm just going to type 2 pi r, then that has to equal to 20 pi. Meaning that I can replace the 2 pi r with this 20 pi. So that means then that dA dt is equal to 20 pi dr dt. All I did there was a substitution. And we know that dr dt is equal to 0.2. So I can just substitute 0.2 in place of that. And when I use my calculator to multiply 20 by 0.2, I get 4 pi. And you just do that on your calculator. You don't have to do it by hand. So we get letter C for number 78. Simple related rate problem. So definitely don't give up on that one. Number 79. For which of the following does the limit as x approaches 4 exist? So when we take a look at the first graph and we approach from the left and from the right, from the left side we're approaching a y value of 3. From the right side we're approaching a y value of 3. So the limit does exist. So that one we're going to keep. And number 2, when we approach from the left side, we're approaching a y value of, looks like 4. And from the right side, we're approaching a y value of 4, so the limit does exist. So we're going to keep that one. Now, in number 1, I didn't mention this. Don't be fooled by this point up here. This is the actual function value. A limit is what we approach, not necessarily what we actually reach. In number 3, when we make our approach from the left side, we're approaching a y value of 4. From the right side, we're approaching, it looks like, a y value that's not 4. So the limit does not exist, so we're not going to keep that one. So we're going to keep 1 and 2, which is letter D. Number 80, the function f is continuous and differentiable. Here we go with the theorem. From -2 to 1, if f of -2, and for me it's helpful to make a sketch of this, so I have -2, 1, 2, 3, 4, 5. And 1, 1, 2, 3, 4. Now remember, we have a function that is continuous and it does have a derivative, and we're looking for a false statement. There exists a value of x between -2 and 1 such that there is a y value of 0. So if we're going to, if the function that connects these 2 points is continuous, then we're clearly going to have to pass through 0 at least once. So that is a true statement. So that is not our answer. That is true. In letter B, there is a value of x between -2 and 1 such that the instant rate of change is equal to 0. So now I'm thinking about Rolle's theorem, or I'm thinking about the mean value theorem. Rolle's theorem is actually a little bit easier because I can say that I can't promise that the derivative will ever be 0 because the 2 endpoints do not have the same y value. So this is a false statement. That's my answer, and there's no need to read the other statements whatsoever. Make sure that you spend time in your reference packet studying the theorems and knowing the conditions. Number 81, let f be the function with a given derivative. So we have the derivative given, and we want to know how many relative extrema. Now, in order for these to be relative extrema, we don't just touch the x-axis, we must cross the x-axis. So what we're doing is we're going to count the number of times that the graph crosses the x-axis. So I'm going to bring up my calculator, and I'm going to put y equal to, I got to turn it on, y equal to, clear, get rid of that. Okay, so I have sine of, remember that your calculator should always be in radian mode when you are working with AP calculus. Did I get that? It's hard for me to type and talk at the same time, but I don't know why I put that in parentheses. Delete. So that's the sine of x squared plus 1, and what we're trying to do is count the number of crosses from 2 to 4. So I'm going to make it easier on myself. I'm going to make the window go from 2 to 4. I'm going to spread that out, and instead of counting by ones, I'm going to count by 0.5. That just spreads the axis out a little bit. And I don't need to go from 0 to 100. I'll just change it back to the standard, which is -10 to 10. And I'll hit graph. Okay, so if we count, there is a cross 1, 2, 3, 4. So this function crosses the x-axis 4 times, so it has 4 relative extrema. Number 82. The rate of change of the altitude of a hot air balloon. Whoops. The rate of change of altitude. So usually H represents, well, let me keep reading. The rate of change of altitude of a hot air balloon is given by, okay, so this function right here, R of t, is the rate of change of the altitude. Which of the following expressions gives the change in the altitude? So remember that word change tells us that we're looking at an integration problem. When you integrate a rate, remember you lose the rate. So we want the change in the altitude during the time that the altitude is decreasing. All right, so let's think about that. If the altitude is decreasing, the rate of altitude is negative. So we're going to have to use our calculator to figure out when. Basically, that means when is R of t less than 0. So let's bring our calculator up. And I'm going to clear the calculator. I'm going to go to y equal to and get rid of that. So I have x cubed minus 4x squared plus 6. Okay, I think I've got that typed in correctly. And we're going to go from 0 to 8. So there's 0, and 8, and I will probably now change this to count by 1. So pay attention to that when you're making your graphs. And let's see, I'm going to put y2 to be 0 because I need to calculate those numbers, the intersections. So I'm going to hit graph. So in this region, we can see that the R of t graph is negative in this region right here. So I'm going to find those 2 points of intersection. Second calc number 5. Remember that the calculator finds the point of intersection that it's closest to. Enter, enter, enter. So I'm going to have a low value of 1.572. So it could be A. It could be, so we already know, all right, so it's multiple choice, I realize that, and we're not having multiple choice in the year 2020, but let's go ahead and do this. So D could be the answer, or A could be the answer. None of the rest of them can be because they don't have the correct lower bound, so those are gone. Now, remember what we said, we want the change in the altitude. So when we integrate the rate, remember R is already the rate. So that's what we want to integrate. It would be very tempting to pick D, but if we integrate R, it takes us back to altitude because R is already the rate of change. So it's one of those situations where I've talked to you before, you can't necessarily trust that the prime is going to be the thing that gives it away. In number 83, the velocity in feet per second of a particle moving along the x-axis is given by this function right here. What is the average? And we can insert value of the particle from time 0 to 3. All right, so now we want to do 1 over b minus a, so we're going to have 1/3 integral from 0 to 3 of v of t, sorry, that's not absolute value, dt. So on the calculator, since I'm just going to do this, use this function for this one thing, I'm going to go to the home screen, clear, and I'm going to do parentheses 1 divided by 3, and then I'm going to do math number 9 because I'm going to do the integral of e raised to the t, close parenthesis, plus t times e to the t in terms of x from 0 to 3, and we get 20.086, which is letter A. Number 84. A pizza heated to a temperature of 350 degrees Fahrenheit is taken out of an oven and placed in a 75 degree Fahrenheit room at time t equal to 0. The temperature of the pizza is changing at a rate of negative 110 e to the 0.4 t degrees Fahrenheit per minute. To the nearest degree, what is the temperature of the pizza at t equal to 5? So this is an initial condition problem. So we're going to need the initial condition, and the initial condition is at time 0, at time 0, the temperature of the pizza is 350 degrees. The 75 degrees has no bearing on the problem whatsoever. It's just telling us that we're putting the pizza in a 75 degree temperature room. So we are going to take the 350 plus, and then we're going to integrate the rate, because remember, we're trying to accumulate temperature, and this is a rate. So we're going to integrate from 0 to 5 of this function right here. So that's going to be our integrand. dt. So with the calculator, again, I'm going to keep it on the home screen. Whoops, clear. So we're going to have 350 plus math 9 of negative 110 e to the negative, be careful here, 0.4 x close in terms of x comma from 0 to 5 close enter, and the pizza is 112 to the nearest degree, 112 degrees Fahrenheit, which is letter A. Number 85, if a trapezoidal sum over approximates the net area and a right Riemann sum under approximates the net area, which of the following could be the graph of f of x? So the first thing that we notice is we have a decreasing function, increase, increase, decrease, increase. So let's think about a right Riemann sum. If we were to put a right rectangle in this one right here, in the first increasing, so the right rectangle would come to here and go over, and that is an over approximation, but this says the right Riemann sum under approximates, so we know it can't be an increasing function because a right Riemann sum will over approximate. So increase, 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 so it's between A and C. So we've eliminated everything we can figure out using a right Riemann sum. Now then it says the trapezoidal rule over approximates. So we have to really carefully draw in the trapezoids to see. And if you look at this first trapezoid that I've already drawn in here, you can see if you carefully sketch that, and I can't carefully sketch it with a mouse, we are over approximating, whereas this one is actually a smidge, well, less than that, a little bit of an under approximation, so our answer is A. So you can do that by drawing. Number 86, we are doing volume of known cross sections. We're not actually doing that in the year 2020. So if you're in that year, you can move the video up a little bit, but I'm going to go ahead and go through this problem for years to come. The base of a solid is in the first quadrant, and we're looking at the graph of y equal inverse tangent, which I'll look at in a second, and the line y equal to 3 and the vertical line x equal to 1. Each cross section is perpendicular to the x-axis, so the first thing I know is that I am in terms of x. That's one thing I know. We're making a square cake, so the area is equal to side squared. And let me move that as an exponent. Okay, so that's the next thing that I know. And I need to know the length of a side. So I'm going to need to look at my graph. So s is equal to, let's take a look at the graph of what that thing looks like. So clear and y equal to and clear, and we have second tangent, so that's inverse tangent of x. And we have the line y, make sure, yeah, we have the line y equal to 3. And let's see what that looks like. Zoom, since it's trig, I'm going to do a zoom 7 window. Okay, so what that is looking like then, we're in the first quadrant. And we have y equal to 3 up here. And let me pull that graph back up. And then inverse tangent looks something like this. And then we have the line x equal to 1, which we don't have on our calculator, but it would look like that. I mean, it would come all the way down, but I'm not going to come all the way down because I don't want to confuse you, because the region is in the first quadrant and it's bounded by the y-axis. So the boundary is here, inverse tangent, which is here, the line y equal to 3, which I did not draw very straight, which is here, and then this region right here. So we're trying to find the area of this region. And so if the cross sections are perpendicular to the x-axis, then we're going to do a top minus bottom. So the top curve is actually the line 3. So if I come back up here, the length of the side is 3, top minus bottom arc 10 of x. All right, so when I do my integral, I'm going to accumulate starting at the lower bound of 0, stopping at the upper bound of 1, and I'm going to take my side, which is 3 minus arc 10 of x, and then I'm going to square that, and I'm going to do that out on the calculator. And so when I do that, so math number 9, integrate, parentheses, 3 minus inverse, whoops, I didn't hit inverse. Yes, I did. Inverse tangent. Clear. Math 9, parentheses, 3 minus inverse tangent of x, close, close, squared, in terms of x from 0 to 1, and I get 6.613, which is B. Number 87. In number 87, we have a function. We have the first derivative given here, and we want the coordinate of the point of inflection. So you need to remember that when f prime of x has a local max or min, f has a point of inflection. That's your All About Me sheet. So I don't really have to go to the second derivative to figure this out. I'm going to grab my calculator and I'm going to pull that out, and I'm going to need to look at a graph on this one. So y equal to, get rid of that, get rid of that. The numerator is parentheses, square root of x, close, close, divided by parentheses, 1 plus x raised to the third power. Okay, and I'm looking for max min, so zoom 6, a standard viewing window. So either I did not type that well, or it's really, really close to the x-axis. So let's check the typing first. Square root of x, okay, that looks good, divided by 1 plus x to the third power. And okay, so I'm going to do a zoom box. I'm going to zoom that up. And we know the answer is either from negative 0.278 to 1.8. So I'm going to move my cursor, zoom box. I'm going to move it past there, move it down. And I'm going to make sure I go past the 1.008. Enter. So there is a local max right there. So I'm going to do second calc, number 4. Enter. Left on the left side, and then on the right side, enter, enter. And I get 0.473, which is letter B. So this was a good opportunity to practice your zoom box skill. Make sure you know how to do that. Number 88, on a closed interval, which of the following could be the graph of a function with the property that the average value is equal to 1? All right, so let's simplify this a little bit over here. 1 over 4 minus 2 is actually the same thing as, of course, 1/2 of the integral from 2 to 4 of f of t dt, I'm sorry I can't write very well with the mouse, equal to 1. Now I can multiply that 2 to the other side and say what I'm really looking for is the graph that has a net area from 2 to 4 underneath of the curve of f of t. And if I multiply both sides by 2, then I get an area of 2. So let's play around. I would, if I were doing, I am doing this. I started to say if I were doing this, I would start here and say, okay, I have a rectangle from 2 to 4. So that's going to be 2 by 2 is 4. So that's not going to be it. Here I have a triangle. Come on, you can do it. So it's 1 by 2. So that area is, did I do that right? From 2 to 3 is 1 times 2 is 2, and half of 2 is 1. And then we have 1 times 2 is 2, and half of that is 1. So 1 plus 1 gives us an area of 2. And you could rule out letter D by doing the area of a trapezoid. Number 88. Actually, we did 88. We're looking at 89. Let f be a differentiable function. So if f is differentiable, you know that that also means that f is continuous. And we have f of 2 is 3 and f of negative 2 is 5. Let g be the function defined by g is equal to x times f of x. Which of the following is the equation of the tangent line? So when we see that, we know that we're going to do y minus y1 is equal to m times x minus x1. And those are subscripts. And we're trying to find the equation of the line tangent to G. All right, so to get the slope, we're going to need G prime. Now G prime, since G is right over here, x times f of x, that is a product. So we're going to need the product rule in order to find that derivative. So we have the first, which is x times the derivative of the second, plus the second times the derivative of the first, which is just 1. And we don't have to write the 1 there, but I'm just doing it for emphasis. And then we wanted to find that value at 2, so we can substitute a 2, substitute a 2, substitute a 2, and substitute a 2. So we know from up here that f of 2 is 3, and we know that f prime of 2 is negative 5. So that's going to be 2 times f prime of 2 is negative 5. I put an equal marks here instead of a plus. I see that now. You probably already saw that. Plus f of 2 is 3 times 1, which is 3. And 2 times negative 5 is negative 10. Negative 10 plus 3 is 7. And it might even be negative 7. That might even be better. And we can see when we look at our tangent lines that only one of the choices has a slope of negative 7. But of course we could substitute the x and the y value when x is, yeah, we would have to find g of 2 by substituting in here. So that gives us a y value of 6. All right, for number 90, for all x in the closed interval 2 to 5, x has a positive first derivative. So if we have a positive first derivative, that means f is increasing, and a negative second derivative. All right, so which of the following could be a table of values for f? So let's get rid of anything that's not increasing. 7, 9, 12, 16. So this one's still in. 7, 11, that one's still in. 16, 12, that's decreasing. 16, 14 is decreasing. 16, so it's between these two right here. Now, one thing we know if we have a negative second derivative is that the graph is concave down. But here's the thing: we don't have the concavity. We can't just plot these points because we don't know how they're connected. So plotting points is definitely not a way to go about this problem. Instead, what I'm going to do, notice that the x values in both cases change by 1, by 1, by 1 in both sets of data. So now I'm going to find the change in y. So the change in y from 7 to 9 is 2. From 9 to 12 is 3. And from 12 to 16 is 4. So those are approximated first derivatives. We're using average rate to approximate instant rate. And notice that these first derivatives are increasing 2, 3, 4 as we move forward. But if the second derivative is negative, that would mean that the first derivative would decrease. All right, so let's check out and make sure that it's going to be b. 11 minus 7 is 4. 14 minus 11 is 3. And look there, we have a decrease. And 16 minus 14 is 2. And notice that those first derivative approximations are decreasing, verifying a negative second derivative. So the answer is B. Number 91, a particle moves along the x-axis so that its acceleration is given if the velocity of the particle is 2 at t equal to 1. So we have an initial condition, 1, 2, and that's the velocity. And we want to find the velocity at t equal to 2. So this is an initial condition problem. So we will have 2 initial condition plus the integral starting at where we left off, which is 1 to 2 of a of t dt. And that's a calculator problem, so we're going to bring that up and on and clear. I'm going to do that on the home screen. So 2 plus math 9 of ln, whoops, delete, 1 plus 2 raised to the t power in terms of x from 1 to 2 is 3.346, which is letter E. Excuse me. And finally, number 92, we have a function whose name is g of x, and it's given by a definite integral from -1 to 3. Which of the following intervals is g decreasing? All about me sheet. So g decreases when g prime of x is negative. So we have a function g is given as a definite integral, so we need the derivative, so that's ftc part 2. So we take out the t, put in the new function, and multiply by the derivative of the new function, making g prime of x equal to sine of x squared and now we want to figure out from -1 to 3, when is g prime of x negative? So we can grab our calculator. Y equal to, get rid of that that's in there, and I have sine of x squared. Clear, let's do that again. Sine of x squared. My window is going to be from -1 to 3, and I'm going to count by 0.5, graph, and there it is right there. So here's our negative region. So I'm going to go back into it and put 0 in as y number 2. I'm going to do a point of intersections, second count 5. And the first value is, enter, 1.722. And that is the only interval that begins with 1.722. This one ends with 1.722, but if you look at the calculator, you can see that we're negative from 1.722 to a number greater than that, which would be 2.507.